Namaskar students. In the previous few videos, we had discussed several aspects of Rolle's theorem. We have seen a few problems regarding Rolle's theorem. In today's video, we shall discuss the statement of Lagrange's mean value theorem. And finally, before ending today's video, we shall try to understand the geometrical interpretation of it. So let us start today's video. So the statement of Lagrange's mean value theorem goes like this. Let there be a function from the closed interval AB to the set of real numbers, a real valued function such that real valued function means the output will be a real number and the domain is the interval closed interval AB such that number one, f is continuous in closed interval AB. Number two, f is differentiable in open interval AB. Then there exists at least one value of x, say C, such that f dash C equal to fb minus fa divided by b minus a, where C belongs to AB. Now let us try to analyze or understand carefully what this statement actually tells. See, the first part of the statement is called hypothesis part. This is the hypothesis. Hypothesis means whatever you are considering. And the next part, that is the outcome, means if you consider this, then the outcome will be this. See, the hypothesis part is somewhat similar to the Rolle's theorem. See, in Rolle's theorem also we had that the function will be a real valued function. If you can recall the Rolle's theorem, the link of that video will be given in the description box. Now, same thing, the function is from AB to R, closed interval AB to R, same thing as Rolle's theorem, and the first two conditions, that is of the hypothesis, the function should be continuous in closed interval AB and the function should be differentiable in open interval AB. That is, f dash will exist in open interval AB. These two conditions are similar to Rolle's theorem conditions. Only that the Rolle's theorem had one extra condition in the hypothesis, that the functional values of f at A and B will be equal, fa equal to fb. That was the third condition which was there in the Rolle's theorem, which is not here in the Lagrange's mean value theorem. So that condition is omitted over here. Lagrange's mean value theorem tells that we don't require the third condition for giving this outcome. Okay, now see what happens if you consider this two things as a hypothesis part, then the outcome is that there will exist at least one value of x, say C, between AB. Now where C belongs to AB means what? The value of C lies between A and B. Okay, value of C lies between A and B, open interval. So C cannot be equal to A and B. The value of C will lie in between A and B, somewhere in between A and B. You will get such a C such that the derivative of the function at that point C will be equal to f of b minus f of a divided by b minus a. Okay. Now see, here comes the interesting part. We'll tell you that this Lagrange's mean value theorem is actually a generalization of Rolle's theorem. Why? What is the meaning of generalization? Generalization means by understanding Lagrange's mean value theorem and putting certain specific conditions into it, you can arrive at Rolle's theorem. See, in Lagrange's mean value theorem, in the hypothesis, you have two conditions. Now, if you add the third condition, that is Fa equal to Fb, which was there in the Rolle's theorem, what will happen? The functional value of b and functional value of a will be equal. So, if Fa is equal to Fb, then Fb minus Fa will be equal to 0. Ultimately, 0 by whatever non-zero part is there, that will be equal to 0. So, f dash c will become equal to 0, which was actually the outcome of Rolle's theorem. In Rolle's theorem, the outcome was that you will get at least one value of x, say c, such that the derivative of the function at that point c will be equal to 0. Now, over here also, Rolle's theorem is a particular case of Lagrange's mean value theorem. Why? So, this comes in the examinations, might come in your examinations, a very short thing, that how can you say that the Rolle's theorem is a particular case of Lagrange's mean value theorem? So, the answer will be, since putting the condition Fa equal to Fp, we get this part equal to 0 and f dash c equal to 0, which is the outcome of the Rolle's theorem. So, we can tell that Lagrange's mean value theorem is the generalization of Rolle's theorem, or the other way around, Rolle's theorem is a particular case of Lagrange's mean value theorem. Now, see, over here also you have to pinpoint one phrase, that is at least. So, the Lagrange's mean value theorem tells that you will get at least one value of x, say c. So, you might get more than one value of x for which this condition, this outcome will hold. So, this theorem does not guarantee the uniqueness of c, but it tells you you will get at least one c. Okay. So, this is the statement that these two conditions are the hypothesis. F will be continuous in closed interval AB, f dash will exist in open interval AB. If these two conditions hold true, then you will get at least one value c of x, such that f dash c will be equal to fb minus fa by b minus a. Now, let us move on to the geometrical interpretation. See, suppose this is the function, okay, any arbitrary function. Now, let us see if this function qualifies the conditions or the hypothesis of the Lagrange's mean value theorem or not. See, this is obviously by seeing, looking at it, if you consider this point as A and this point as B, okay. Now, if you consider this point as A, this point as B, this is the function, this is the x-axis. See, between A and B, including the points A and B, this function is continuous. There is no break of this function, or the function does not move towards the infinity at any point between A and B. So, you can tell the function is continuous in closed interval AB, including A and B, the boundary points. Also, see, the function is very smooth curve over here. So, there are no sharp points, sharp vertex like points over here. So, the function will be differentiable also. Hence, these two conditions of the Lagrange's mean value theorem holds true for this function. So, this function qualifies to be a function to be set as an example of Lagrange's mean value theorem. Now, see what happens. So, this, since this is a function fx, okay, this height will be fa from point A till this much. This will be fa. From point B till this much will be fb. This height will be fb. Now, what will happen if you connect these 2 points, and let us draw a line parallel from here, a line parallel to the x-axis. So if I tell you somewhere over here you will have this angle as theta. This line, if you extend, it will cut the x-axis somewhere at this point, angle theta. Now since this line is parallel to this line, this angle will also be theta. Okay. So we all know by the geometry, whatever we had learnt in school level, that is the slope of this line. Slope of this line will be tan theta. There is no issue with that. So let us name this line. Suppose this point I am telling M N. This point, say this is P. Okay. So slope of Mn will be tan theta. I hope there is no issue with that. Okay. Now what is the distance of line MP? What is MP? This MP is nothing but B minus A. This distance is nothing but this distance. Okay. If this distance is B minus A, this is also B minus A, because this is B, this is A. So this distance will be B minus A. Since this is B minus A and this is same as this, these two are equal. So MP will be B minus A. Similarly, what is NP? NP means this part. See, NP is this total line minus this, means this minus this. Okay, what is this total? FB minus this part. See, this part is now equal to this part. Okay, what is this part? This length, FA. So NP will be FB minus this, that is FA. So FB minus FA. Now see, slope of Mn, therefore slope of Mn equal to tan theta equal to, by normal laws of trigonometry, tan theta means what? If this is a right angle, this is a right angle triangle, this is a right angle triangle. Okay, now what is tan theta? Tan theta means perpendicular by base. So NP by MP, that is equal to, what is NP? FB minus FA by B minus A. So the slope of Mn is nothing but FB minus FA by B minus A. This is what we are getting, the slope of Mn. Now if you look carefully, see, and suppose you move this line downwards, do not change the slope, you see, you will get a parallel line, a line parallel to Mn over here, which touches the curve fx at one particular point, say this. You will get, always you will get, if you move this one parallelly downside, see, ultimately at one point you will get to touch, just touch this function fx, this curve fx, and the line will be nothing but parallel to the line Mn. Now see, the slope of this line, since it is parallel to Mn, will also be same as the slope of Mn. Since these two lines are parallel, the slope of these two lines will be equal. Now see, At this point, let us name this point as C. The point at which this line touches the curve fx. Now, if I tell you, forget about whatever slope you have got. At a particular point C, that point, if you just project it upwards, it will touch this function at some point. Okay. So if I tell you slope of this line, there is another way to find out slope of this line. That also we had learned in school level. That is f dash c. Derivative of the function at the point C will be nothing but slope of this line. So we can tell slope of this line is f dash c. Now slope of this line is also equal to slope of this line, and what did we get the slope of this line? Fb minus fa by b minus a. See, that is the outcome of Lagrange's mean value theorem. So Lagrange's mean value theorem tells nothing but that is, if the function is like this, that is the function satisfies the Lagrange's mean value theorem class of functions, then you will get at least one point C whose slope will be equal to the slope of this line. Okay, this is the geometrical interpretation of Lagrange's mean value theorem. Now say, apart from this form, there are a few other forms also by which you can represent Lagrange's mean value theorem. But you have to understand, this is the general form. All other forms that we will discuss right now are particular cases that will be used in very special occasions. See, if you consider the distance between A and B as h, then from here you can tell, therefore B equal to A plus h. So from A, if this distance is h, if you have to reach B, you have to do A plus 1 into h, 1h. Now C, since lies between A and B, you can write C equal to A plus some theta into h, where this theta lies between the number 0 and 1. Why? See, if you consider theta as 0, then C will become equal to A, that is this boundary point. If you consider theta as 1, okay, so C will be A plus 1 into h, that is C equal to A plus h means B, so C will become equal to B, that is the final boundary point. So C neither lies in this boundary nor lies in that boundary. C is somewhere between A and B, hence the multiplying factor of h will be neither 0 nor 1, somewhere in between 0 and 1, this. So you can represent C as A plus theta h. Now considering this, if you put the values over here, if you put the expressions of C and B over here, what do you get? We get f dash A plus theta h equal to Fb means f of A plus h minus Fa by B minus A means h, or you can write this one as, see, if you put h this side, you get h f dash A plus theta h equal to f A plus h minus Fa. Just jumbling the sides here and there, ultimately you see you can get f of A plus h equal to Fa plus h f dash A plus theta h, where theta lies between 0 and 1. Okay, this is a very interesting form. See, by this form you can find out the value of the function after A. If you know how much distance you have to travel, that is h, and the functional value, the derivative functional value at that point c. Okay, so in either case, whatever you interpret, whatever you analyze, this is another form of Lagrange's mean value theorem. If you consider the distance between a and b to be h and c equal to a plus theta h. So if you consider b minus a equal to h, you get this. We have seen just now. Now see over here also, if you consider a as 0 and h to be x, what happens? This one becomes a 0 and h is x, so this is fx, 0 plus x fx, f of 0 plus x, f dash a is 0, theta x, where theta lies between 0 and 1. So this is another form of Lagrange's mean value theorem if you consider a as 0 and h to be x. This is also a very interesting form. This form actually gives a type of formulation. If you don't know the function fx, this form C actually gives you the formulation of how to find out fx. Fx is nothing but the functional value of x at the point 0 plus x into the derivative of the function at the point theta, where theta lies between 0 and 1. So these were the different aspects, preliminary introductory aspects of Lagrange's mean value theorem. So my dear students, if you have understood today's video, do share this video with your friends, subscribe to my channel, and don't forget to follow my page. Till then, goodbye.